Hello there, class. This is an example problem covering Unit 4.3. And in Unit 4.3, we're learning about the moments of forces about a specific axis. So this is just taking what we've learned before about moments in Unit 4.1 and 4.2, and we're just adding basically an extra step to not just find the moment about a point, but a moment about a specific axis. So this problem is taken from the 13th edition of the book. It's problem 4-60. And this is what the diagram in the book looks like. You kind of have this angle iron attached to a wall by a bracket, sort of a thing. So I've drawn a simplified version here on the board. So I just have the dimensions. We have this angle iron at the tip. Up here, we have a force, and we're given the coordinate direction angles for that force. And then we have this AA axis. And so what the problem is asking us to find is the moment of the force about the axis AA, which is this, where it's mounted to the wall. And then to make things more interesting, we're going to also find a different set of coordinate direction angles that maximize the moment about the AA axis, and then we'll find that. So this is kind of a fun one, a little bit more involved than maybe some of the things you'll have to do, but hopefully it's informative and you learn a few things. So like we learned about with the moments of forces in 3D, to find a moment in 3D, it's usually easiest to use the cross product, which means we need to find the position vector that goes from the axis of rotation to the line of action of the force. So essentially, anywhere along this axis AA to point O, where the force acts. So we're going to go basically find the position vector from A to O, and we're going to cross that with the force vector up here, and that will find us the moment about point A. And then there's just one more step we have to do to find the moment about the axis that point A lies on, instead of just about point A. So let's do that. So I'm going to start by finding the position vector. So position vector from A to O. So we can just walk along. In the x direction, we're going to go in negative 100 millimeters. And the y direction, we go 0. And then in the z direction, we go plus 100, plus 50, so plus 150. So that equation 1, we'll come back to that. Now we need to find the force vector. So we use that. Find that just like we would solve any vector. We've done this several times now with coordinate direction angles. So the force vector is going to be the magnitude of the force times the cosine of the x component, the cosine of alpha is 60, the x component, plus magnitude times cosine of beta is also 60, plus the magnitude times the cosine of gamma, which is 45. And then if we just plug in the numbers, get that force is 15 pi plus 15 J plus 21 K, and that is units of newtons. We'll call that equation 2. So we know that the moment about point A is just going to be that position vector crossed with that force vector. Set up our cross product box here. 100, 0, 50, 15, 15, 21. We've set it up now. Now we just solve it out. And you'll remember that when we do this, what we'll do is we're looking for the I, so we cover up the I column. We're going to take this value times this value minus this value times this value. That gets me 0 minus 15 times 150. That's the z x component, and then for the j, it's minus. Cover that up. Take this value times this value minus this value times this value. So we get negative 21.21 minus 15.50. That's the y component. And then for the z component plus, again, the thing, we cover that up. 100 minus 15 times 15 minus 15. 0. 115 minus 15 times 0. And then when I do the math on that, I get the moment about A equals minus 2,250 in the x direction plus 4,371 in the y minus 1,500 in the z as means of unit millimeters. Now, that's not the final answer, right? That's the moment about A. We aren't looking for the moment about A. We're looking about the moment about this axis. So if we were to draw what that moment about A was as a vector, right? So we have this vector notation. It would be going in sort of, oh boy, it's going to be tricky to draw. So it'd be going in the negative x, positive y, negative. So it might be kind of going kind of in like this. Golly, I'm not going to be able to draw this very well. But it's basically going to be going in this direction, right? It's going to be trying to twist about point A in this this kind of 3D direction. Yeah, it's going to kind of cause a twist, you know, into the board like this, right? It's going to try to twist it like that. You probably can't visualize that super well, but what we need to do is find the component of that vector that lines up with the axis we're going to rotate about, AA. So we've seen this before with the dot product, right? We can use the dot product to find how much a vector, how much direction a vector shares with another vector. So what we want to do is we want to find the unit vector for the axis, AA, and dot that with this moment about point A. And that will tell us how much of this vector, which, you know, is going in this goofy direction, is actually causing a twist about the axis. That's what we're trying to solve. So the unit vector, AA, is in this case really simple because it is just in the y direction. So we can just call it 1j. And what we're going to find is we're going to say the moment, you can still see that, right? Yep. The moment about AA is going to equal moment of about A dotted with the unit vector device. So and what I end up getting is that the moment of because when you do the dot product, you just multiply the like components. So there's a 0 in the x, so that's nothing. 1 in the j, so we get the 4,371, and it's 0 in the z, so that's nothing. So we just end up with 4,371 Newton millimeters. So that is how much of this moment vector causes a twist about this axis, which in this case is just the y-axis. So that's the first part of the problem. That wasn't too bad, really, right? It's just do what you've done already, and then just remember you got to do some dot producting to get then magnitude or about a specific axis. Now this next part, this is a little bit trickier. This is more of a thought exercise. You probably won't see any problems like this in your homework, but it's good to kind of understand, what are we doing? So, right, it's saying we're going to try to figure out how would we position this vector to cause the biggest possible moment about the AA axis. And to do that, basically, we know that a moment is largest when the position vector and the force vector are perpendicular to each other, right? If I have, if this is my point that I'm rotating about, and this is my position vector, and this is my force vector, this is going to cause a larger twist than it looked like this, right? This will cause a smaller twist. So, right, assuming that these are all the same magnitudes. So when this force is perpendicular to the position vector, this will be bigger. So basically, we need to find, we already know our position vector. We need to find the force that makes that perpendicular to that position vector. And we don't, basically we want to maximize the y component of this moment, since we already saw that the y component is the only thing that's kept. We want to maximize the y component of the resulting moment. So to do that, we kind of have to match up the x and z components of this force to be perpendicular with the x and z components of the position vector. So hopefully that kind of makes sense conceptually what we're trying to do. So the way that we can kind of think about this is we have, so this is our position vector, right? It has, right, it's 150 tall, 100 deep. So we need to, a little bit tricky to kind of talk through, but we want our alpha, or our angle from x, to be square with that. Basically, we need it to match let me think about this. Even writing it down and having done this earlier, I still got to think about what I did, how I got there. We want it to match that angle. That'll make it square. So alpha is going to equal the inverse tangent of 100 over 150. Going to get us 33.69 degrees. and gamma is just going to be 90 minus that. That's going to be 6.31 degrees, right? So the force vector will have no y component because the y component of the force doesn't contribute to the y component of the moment at all. So we're going to be taking this away, and we'd be making this $33.69. We're making this, since there's no y, this is just going to be 90 minus that, 56.31. All right, hopefully you can kind of see that would make it stick perpendicular to that. And it may be a bit of a case of trial and error of just drawing triangles and figuring that out if you weren't sure exactly what you're doing. But that's conceptually the idea. So what is that force? What is that moment about the axis when we do it that way? Well, so that would change our force vector. So it's now 30 cosine 33.69 pi plus 30 cosine 56.31 k hat z direction, which equals 24.96 plus 16.64. And then we just take the cross product. So we get the moment of A is equal to the little cross product box. And that gets us 5,408 in the J. So right, we optimize this to make sure there's we don't want to waste any moment in the X or Z direction, so they don't maximize our moment about the axis. So then we just take the dot product again. So the moment about axis AA equals moment A dotted with unit vector AA, which just gives us 5,408 Newton millimeters. And there we go. Those are the answers. So hopefully I didn't confuse you more by doing that. But that's the idea with these forces about axes, just building on what we did in 4.2, adding essentially another step. So hopefully that was helpful. Thanks.